In this chapter, we're going to be discussing reaction kinetics. And kinetics are simply how quickly a reaction takes place. You're already familiar with this, even though you may not be aware of it. Some reactions take place very, very quickly, such as explosions, fireworks. Those reactions take place at a very fast rate, whereas a reaction such as rusting or corrosion takes place at a very, very slow rate. So sometimes we want to make a reaction go faster than it normally would, or we may for some reason want to slow it down more than it would normally take place. And so that's what this chapter is going to be about. How do we measure reaction rates, and how do we get those reaction rates to change? What factors can we manipulate in order to change a reaction rate? So to define what the rate of a reaction is, we define it as the change in concentration. And you remember the Greek letter delta is the Greek letter that we use to indicate a change in something. We use that in our calorimetry chapter. So it's going to be a change in concentration of some reactant or some product. And we use brackets to indicate the concentration of some reactant or some product divided by the change in time. And since concentration is normally expressed in molarity, we're going to use seconds for our unit of time. So the reaction rate is going to be in molarity per second. So because the change in something, as you learned before, is always the final minus the initial. One thing that we want to be true is we always want our rate to be positive. And so it's going to depend whether we need to put a negative sign in front of here, whether we're measuring a product or whether we're measuring a reactant. If you are measuring a reactant, the concentration of a reactant is going to decrease as you progress through the reaction because your reactants are going to turn into products. So there's less reactant at the end than there was at the beginning. So if you take final minus initial, that's going to give you a negative number. Well, because we want our reaction rate to be positive, if you use the concentration of reactants in this particular formula, you're going to need to make it negative so that the rate will turn out positive. On the other hand, since the concentration of products is going to increase, that means the final will be greater than the initial. And so if you're using a product concentration, then you don't make it negative, you're going to leave it positive, and that will also make the reaction rate positive as well. We're going to get some practice using this definition of reaction rate. He expects you to do some problems like this in your book, but he doesn't really give you any examples, so I would like to work an example problem for you. The document that I sent you that has sample problems for videos does have one for video number 1. So if you have that next year, if you need to go find it, we will look at this first example. In a kinetics study, the rate of a chemical reaction is 0.5 molarity per second. The concentration of a product at t equals 2 seconds was 1.6 molar. The next concentration recorded was 3.7 molar, but the student forgot to record the time. What should it have been? Okay, so we're going to use our reaction rate definition here. And we already know that the rate of reaction was 0.57 molarity per second, okay? So we're looking for the change in concentration, and we know that it starts out at 1.6 and then it ends up at 3.7. Now remember, using a change in means we go from final and then we subtract the initial from it. So the second concentration was 3.7 and the initial concentration was 1.6 molar. Okay. Now, then it says that he made the first measurement at 2.0 seconds, but he forgot to record the time for the second concentration. So that means we don't know the final one, but we do know the initial one. So this is going to be x minus 2.0 seconds. Okay, now you've got to remember a little bit of algebra in order to solve this. You've got your x in the bottom of the denominator, which is not the easiest place to solve an equation. So what I would do is I would multiply both sides by this quantity x minus 2 seconds. So on this side of the equation, I'm going to have 0.57 molarity per second times x minus 2.0 seconds equals 3.7 minus 1.6 gives me 2.1 molar, okay? Probably should have parentheses around that because that is going to be your change in concentration, okay? Now, two ways you could go about this. I know a lot of times in algebra we do use the distributive property to get rid of parentheses, but in this particular case I think what's actually easier is to divide both sides by 0.57 molarity per second. So on this side, if I divide by 0.57, that's going to leave me with x minus 2.0 seconds over here. If I take 2.1 divided by 0.57, the molarities are going to cancel out, and that's going to give me 3.7 seconds on this side. Okay? So now I can add 2 seconds to each side of the equation, and that will give me a time of 5.7 seconds. So this particular student measured the second concentration at 5.7 seconds. Okay? You will have a couple of different problems to do like that in your homework today. So given that example, hopefully that won't give you any difficulty.